So now we're going to start looking at logarithms. So I've mentioned that logarithms are the inverse function of the exponential functions. In other words, logarithms are kind of like an inverse operation of the exponent. So if we think about something like 2 to the x equals 5. So if we think about this kind of equation, how we might go about solving it. Well, there's not really a good way to do it, right? We're trying to think of 2 to what number is equal to 5. And if this is like a something that would be like a whole number, maybe we could guess it. Like if we have something like 2 to the x equals 4, then we could guess that x is equal to 2, right? Or 2 to the x equals 32. Maybe a little bit less well known, but we can still figure out that x is equal to 5 just by testing the powers of 2. But we don't have to raise 2 to a whole number power. We can raise it to a rational number, a negative number. We can even raise it to irrational numbers. We didn't discuss that in the property of exponents videos, but you just put them in the calculator basically because there's not really much we can do with them by hand. But they still are viable numbers. So what do we do in this case? Okay, we can do a little bit of guesswork, right? We already saw 2 to the x equals 4 means x equals 2. If we have 2 to the x equals 8, we know x equals 3. So we know it's somewhere between 2 and 3, and probably closer to 2, but that's about as far as we can get. So we need another operation, another function to define in order to solve problems like this, right? Wherever something that'll solve for the exponent in these problems. This is where logarithms come into play. Okay. So in general, if we have something like b to the y equals x, okay, so b is our base, y is our exponent, x is the answer, we can change this into a logarithm. So this sign means that these are equivalent as log with base b of x equals y. Okay. So note how the parts change. All the parts are the same. Like we have the same parts, they're just in different places. So the b is the base in the exponent. It's also the base in the logarithm. We write it as a subscript of the log. The answer in the exponent equation becomes what we call the argument in the logarithm equation. Okay. So something inside the parentheses like this that's being input into the logarithm, we call that an argument. If you've ever done any kind of programming, right, it's like the same kind of terminology used there for functions because we're thinking of this as the logarithmic function. And then the exponent here becomes the answer. Okay, so we have base, exponent, answer, base, exponent, answer. Okay. So if we look at some logarithms and think about how we might go about solving them, okay, so log base 2 of 8, for example. So we don't always have to write the parentheses here if it's pretty clear what's in there. If you have something like log base 2 of x plus 3, it's probably a good idea to specify if you want the parentheses around the whole thing or if you are putting the parentheses just around x. Okay. So just a little notational thing there. So log base 2 of 8, well, the way we solve this is just by thinking of it in the exponent form, which is that 2 to what power is equal to 8. So we look at the base, we look at the argument, and we think, okay, this raised to what power will give us this? So in this case, we'll get 3. Okay. If we do something like log of 16 of 1/4, okay, a little trickier here. We're saying 16 to what power equals 1/4. Okay, so we know that it has to be negative, first of all, because that one of them is like the reciprocal of the other, right? Not the actual reciprocal, but some power, and then the reciprocal of it. And then to get to 4 from 16, we would take the square root. So this is going to be to the negative 1/2. Okay, so this logarithm is equal to negative 1/2. So one thing we can note from this right away, we can get negative answers for logarithms. What about negative inputs? Can we put a negative number into a logarithm? Okay. Let's just say like log base 2 of negative 2, for example. Well, we're saying 2 to what power equals negative 2. So the most natural candidate might be a negative exponent, but we saw those don't make the number negative. Those give you the reciprocal of the number. So those are out. And there's not really any other candidates. So we can see that there is no number that will satisfy this. So this is undefined. Okay. So we cannot put a negative number into a logarithm. We'll get a similar thing with 0 here. Okay, we're saying 2 to what power equals 0. Again, the most likely candidate would be 0, but 2 to the 0th is equal to 1. So this is also undefined. There's no number that we can put in for an exponent that will give us 0. Okay. Unless, of course, the base was 0, but we actually don't allow the base to be 0. So we do have some restrictions on the base here. So namely, maybe I'll go back up and we can add it to right here. You say that b has to be greater than 0. And also b cannot be 1. Why not? Well, again, let's think about that. Log of 1 of, I don't know, say 2. Okay. 1 to what power equals 2? Well, again, 1 is kind of special because if we raise it to any exponent, it's going to be 1. So there's no answer here either, right? So this is not defined. So we don't allow the base to be 1. Okay. We don't allow the base to be 0, negative, or 1. So it can be anything else. And it's just because the logarithms, again, are the inverse of the exponents. And it gives us an exponential equation, which is nonsensical. Okay. So to kind of summarize here, okay, so the log base b of x, if we think of it as a function, okay, then we can kind of think of its domain and range. The domain is going to be 0 to infinity. Okay. So we can't plug in 0 and we can't plug in any negative numbers. So keep in mind the variable here is x, and this is for any base b. The range is actually going to be negative infinity to infinity. So you can get out any number. Again, this is the inverse function of an exponent. So if we think about the function g of x equals b to the x power, the domain of this is all real numbers, and the range would be 0 to infinity, assuming that b is greater than 0 and not 1. Okay. So we can see the domain and the range flip as we expect to happen with inverse functions. Okay. Now, a lot of times in practice, we don't even really bother specifying the base because a lot of times when these come up, it actually doesn't really matter what the base is. We just need the logarithm. It could be any base. But regardless, there are some common choices for bases. Okay. So some common bases, and there's one that's the most common by far, which is base e. Okay, so e, I'm trying to remember if this number has come up, but this is 2.718. Approximately, it's actually an infinite decimal. It's an irrational number, kind of like pi, right? How pi is 3.14. So e is known as Euler's number, or sometimes just as the exponential number. This is a very common base for both exponents and logarithms, and we'll see in calculus kind of why that's true, and it's that it's its own derivative, which means that its rate of change is the same as the original function, which is a very special property. It makes it come up all over the place. So this is by far the most common base that we use for logarithms. And actually, it's so common that we have a special name for it. Log base e of x is equal to the natural log of x. Okay, so this is read as the natural log, ln. Okay, I always use a cursive L in logarithms so that they're not confused with ones. It's just kind of a habit that I picked up from someone, and it makes it easier to read, in my opinion. So anyway, but though this is technically the natural log, it's very common to just write log of x and mean the natural log. Okay. Historically, when you just wrote the log of x with no base, it actually meant that it was base 10. Okay. So log base 10 of x. And this is actually known as the common logarithm. So the reason that this one was so popular is because logarithms were actually used to simplify calculations done by hand, and our number system is in base 10. So base 10 made the most sense for a lot of calculations. So they would kind of get everything into log base 10. But we don't really do that nowadays with the advent of calculators and computers. So this one is kind of fallen out of style. There's not really much use for it anymore. So nowadays, when people write the log of x, it most commonly means the natural log. I still just kind of write the natural log just for clarity purposes. But if you see the log of x, you can try to infer from the context what it means, but it probably means the natural log. If it's something older, then it probably means log base 10. If it's on your calculator and it doesn't specify, it probably does mean log base 10, and it probably has a separate button for natural log. So these are the most common two, probably. Like, the only place you really see log base 10 again is in older things or in your calculators. Usually there's a separate button for natural log, but this is the most common one by far. Sometimes in computer science, you might use base 2. Okay. But that's not something that we'll really see too much. So that's probably the next most common one, though. But in general, like I said, we probably don't care what the logarithm is, or what the base of the logarithm is. But if we do, it's probably because we need base e.